Thank you very much for Chairperson. First, I'd like to thank any organizers of this conference to give me an opportunity to speak, to introduce my recent work. I'm in the field of ceramics processing, and I'm not so much familiar with the magnetic property of magnetic materials. But now we are using the very strong magnetic field to make crystalline-oriented ceramics to improve their properties. So today I will introduce some of the examples that we have investigated in our laboratory. This is the outline. First, I introduced the texture control in polycrystalline materials, and we apply colloidal processing in the magnetic field. So then we explain I explained this. And I introduced some examples, and finally I introduced the application of our technique to fabricate crystalline-oriented iron oxides, ferromagnetic materials. Basically, in the field, bulk ceramics is prepared from the sintering of ceramics powder. In this case, a ceramic powder should be consolidated in a green cake and then sintered. So in most cases, ceramics material must have randomly oriented, because the powder is randomly oriented in the form of the green cake. But if all the crystallites are well ordered or well oriented in a bulk body, even the polycrystalline ceramics may show the quite excellent properties, which is equivalent to pseudo single crystal. So texturing of the polycrystalline ceramics is very important to improve their many properties. So for making that kind of a crystalline structure, we are using a strong magnetic field. This slide shows the theory of the crystalline orientation using the anisotropic magnetic property. As you know, many materials which has asymmetric crystal structure, that means non-cubic crystal structure, those materials has magnetic anisotropy depending on the crystalline structures. And if those asymmetric crystalline structure materials is placed in a magnetic field, easy magnetization axis is aligned along the upright magnetic field, like this. But easy magnetization axis is differs depending on the materials. So in this case, for example, C-axis may oriented along the field lines, but in this case, C-axis may orient along the perpendicularly applied magnetic fields. So direction is very depends on the magnetic susceptibility of the material. Next slide shows the example of how particle will be oriented in a strong magnetic field. This is just a demonstration using the graphite as a pencil lead and the nylon fishing line. This graphite or pencil lead is dispersed in a liquid, which density is close to the graphite, so it seems to be very well dispersed like that. In the case of nylon, the direction of the orientation is different. Like that. So by applying the external magnetic field, we can control the orientation direction of the particles. In the case of in the case of graphite, magnetic anisotropy is relatively high. So we don't need so much high magnetic field. So orientation will be achieved by using just a neodymium magnet. But in most cases, we are applying this technique for ceramics orientation. For example, in the case of alumina, this magnetic anisotropy is quite small. So, and it depends on the particle size. Basically, we apply this technique. Firstly, the particle should be dispersed in the liquid to make the particle easily rotate in the liquid. So, in most cases, for the stable colloidal solution, we need to optimize the particle size smaller than about 1 micron or less. And sometimes we use 0.1 micron, 0.2 micron. So, for example, 0.2 micron alumina, to achieve the crystalline orientation, we require about 7 Tesla of magnetic field. That's the reason why use a superconducting magnet to achieve that kind of crystalline orientation. The important point 3, the crystal must have asymmetric crystalline structure, because if the material has a cubic structure, it doesn't have easy magnetization access, so orientation is difficult. And also, energy of anisotropy must be higher than the energy of thermal motion, otherwise the particle will be redispersed even applying the magnetic field. And one more important thing is each particle should be single crystalline and completely deflocculated, like that. If the particle has many crystallites in one particle, it is difficult to define the direction of the orientation. So our technique is quite simple. First, we just put the particle, ceramic powder in a liquid. In most cases, we just put it in water or ethanol, or in the case of organic solvent. And first, we make a well-dispersed suspension. To make well-dispersed suspension, we sometimes use polyelectrolyte to improve the surface charging potential, or just changing the pH to give the higher value of the data potential. And then we just put the suspension in a porous mold, which is placed at the center of a superconducting magnet, like that. So, but in the magnet, each particle oriented with applying the magnetic field, then it is sedimented or consolidated like that. So we can make the crystalline oriented dense cake by using this technique. Or in different way, we also can use electrophoretic deposition technique. In this case, first magnetic fields applied to make each particle orient one direction. Then electric field is applied to deposit, to carry and move that particles while retaining their orientation along the field line. So by using that kind of technique, this is the example of textured alumina ceramics fabricated by electrophoretic deposition. This is the microstructure, and this is the XRD of the top surface and the side surface of the sintered body. If this alumina is consolidated without applying the magnetic field, it shows quite randomly oriented microstructure. But if the magnetic field is applied, in this case 12 Tesla is applied, it shows quite very well crystalline oriented structure. In this case, in the case of alumina, C-axis of alumina, hexagonal structure of alumina is aligned along the applied magnetic field. So 006, 1010, and 0012 peaks are quite strongly observed on the surface. And in this case, the side surface 110, 300, 220, these peaks are strongly observed for the side surface like this. shows the EBSD mapping of the crystalline-oriented microstructure of alumina. If the magnetic field is not applied for consolidating during the consolidation, it shows a randomly oriented structure. But if it is consolidated in a strong magnetic field, it shows a quite well-oriented microstructure like this. So in this case, the alumina, hexagonal alumina is aligned like this. C-axis of alumina is aligned applied to the magnetic field. By using this technique, we are trying to improve the many properties of ceramics, different field of ceramics. For example, this is the example of a lead-free dielectric material. This is one of the candidates which will be replaced to the PZT, non-lead PZT. But this shows still lower dielectric property. So, but when magnetic field is applied during the consolidation, we could demonstrate the dielectric property could be improved like this. Or this is the case. This is the example of the thermoelectric module, which is laminated structure, which shows laminated structure. In this case, this layer is aligned magnetic field. So by making that kind of oriented structure or laminated structure, we could show the improvement of the thermoelectric property. Other example is the application of photocatalytic property of anatase particles. In this case, anatase is a completely spherical particle like that, but it is deposited under magnetic field, 12 Tesla magnetic field. It oriented like that. So by making by preparing the crystalline oriented layer, we could demonstrate that photocatalytic property could be improved like this. TiO2 also show the photoelectrode property. So by controlling microstructure, we could demonstrate it that photocurrent shows the improvement depending on the crystalline oriented direction. Our technique using the using a magnetic field and electric field is more extended to control the crystalline oriented direction by controlling the angle of magnetic field and the electric field. In this experiment, magnetic field fixed the crystalline orientation. But by changing the angle of electric field, the particle moves along the electric field lines while retaining the orientation along the magnetic field like that. So by controlling this angle, we can control the crystalline oriented structure like this. This is an example that we use the alumina. By controlling the angle, we can prepare differently crystalline oriented thin layers like this. For example, in the case of the angle is 0 degree, particle is completely C-axis oriented. So C-plane, the XRD peak of C-plane is dominant like this. But if the angle is 45 degree, in this case, plane of 116 is the strongest peak. The 116 plane is the alignment from the basal plane with the angle of 42.31. So by changing the angle, we can demonstrate the differently crystalline oriented layered structure without using any special substrate. By using this technique, we can make the laminar structure. I'm sorry. first layer is deposited like that. The second layer by changing the angle and by repeating the angle B and E, magnetic field and electric field, we can make that kind of laminar differently crystalline-oriented laminar structure. This is an example of the EBSD mapping and the actual SEM photograph. So even from SEM microstructure, we can see a very beautiful laminar structure like this. And then the orientation is completely confirmed by EBSD like this. By repeating many times, we can control the microstructure like this. So the primary purpose we're making that kind of differently oriented laminar structure is to improve the both toughness and the bending stress for material. So by controlling the kind of microstructure, we could show the crack deflection during the bending test. So during the diffraction of the crack, the energy of fracture is absorbed in the matrix of the material. So like oyster shell. So by controlling the crystal structure of each layer like this, we could show we could improve both bending stress and toughness for normally brittle ceramic material. Like that. Another technique to control the crystalline orientation is the use of rotating magnetic field. First, I explained to you that the easy magnetization axis is very dependent on the material. So, for example, if the easy magnetization axis is the C-axis, control of the C-axis or range of the C plane is very easy. But in the case of easy magnetization is A or B axis, it is quite difficult to control C axis. So to achieve the C axis orientation for this material, we are trying to special technique. We are using a special technique like this. First, I explained it using this pen. Suppose this is the C axis, and this is the direction of the applied magnetic field. When the magnetic field is applied this material may be aligned like this. But if the C axis is not the easy magnetization axis, it will align like this. So by applying the magnetic field like this, but it is the C axis is aligned like this. But the problem is control the direction is difficult because it may orient it like this, it may orient it like this, it may orient it like this, it may orient it like this. So C-axis direction is everywhere, every direction. So to achieve the C-axis orientation for these materials, we are trying to apply the magnetic field horizontally like this. In this case, it may stand like this. Some particle may stand, C-axis may stand, but some particle may still be aligned, maybe. So, but even there are some particles which aligns like this. If the applied magnetic field is changed, the direction of the applied magnetic field is changed from this direction, we can control the stand this. But still, it may align like that. So, if we apply the magnetic field from this direction, it may stand like that. So by controlling the direction applied magnetic field direction like that, the C-axis may be gradually stand and become one direction orientation like this. But by changing, but changing the applied magnetic field is quite difficult. So we are trying to rotate suspension itself in a magnet. This is our technique. We put we make the stage and put in a magnet in a superconducting magnet and rotate it. This is the case of electrophoretic deposition. This is shows the simple slip casting. So by applying the magnetic field, we can control the C-axis direction. We demonstrate this is the case by using the zinc oxide. In the case of zinc oxide, C-axis is difficult, hard magnetization axis. So basically, at the top, no c-axis orientation observed like that. But the side surface, only 004 peak is still very weak like that. So by applying the magnetic field from the direction the horizontal, in this case the c-axis is is randomly oriented like that. But by using the technique of rotating magnetic field, we could demonstrate that quite beautifully c-axis is oriented in one direction, like this. We have applied this technique to make the orientation of several kinds of ceramics like this. These materials are for dielectric property application. This is for lithium-ion battery or photocatalyst or other things, engineering ceramics or like that. But I think that my great interest is how we can apply this technique to fabricate ferromagnetic material. So the half of my talk, I will introduce the fabrication of textured iron oxides by magnetic field assisted colloidal processing. As I explained to you first, basically this technique is applied to non-cubic material. And the other point is basically we use diamagnetic material or paramagnetic material. Because if this strong magnetic field is applied to ferromagnetic material, it makes a chain structure and will be difficult to consolidate quite high density. So first our trial is how we can make quite high dense ferromagnetic material by applying this technique. So first I applied this technique to make crystalline oriented hematite. I think it's not necessary to say here in this place. Hematite is the most stable, chemically or thermally stable iron oxide among the many kinds of iron oxides. And hematite is so used for many fields like this. But magnetic property, electric property, photochemical properties are not that high. But my interest is those properties could be improved by making the orientation of the hematite. But actually, first we tried to make a slip casting technique to make the consolidation of hematite cake. First, I met difficulty to make dense green body because of the anti-ferromagnetic property or weak ferromagnetic material property. At room temperature, it shows quite high ferromagnetic. It shows weakly ferromagnetic property, so it makes the chain structure and could not. It's very difficult to make a dense body. So first we need to think how we can make a dense body of the hematite. So I looked at this phase diagram of iron oxide hydroxide system. Here, hematite is the most stable phase of iron oxide. This here is iron, and it is oxidized in different structure, different phases, different structure like this. And looking at this figure, I thought that hematite has high magnetic property, but the precursor of FeOOH or iron oxyhydroxide is paramagnetic property. It shows paramagnetic property, and Among them, for example, most well-known FeOOH is alpha FeOOH or goethite. Goethite has orthorhombic structure and paramagnet. So I thought that if we start this material, we could make the crystalline-oriented iron oxide. And another important point is the phase transformation from alpha FeOOH to alpha Fe2O3 is topotactic transformation. Here it shows the topotactic transformation. Topotactic formation or transition is the phase transition between goethite hematite. And it is a transition in which the crystal lattice of the product phase show one or more crystallographically equivalent orientational relationship to the crystal lattice of the permanent of the parent base phase. So so I thought that if the goethite is crystalline consolidated with crystalline oriented structure, that orientation might proceed, still kept even after phase formation to hematite, alpha Fe2O3. So we use this technique by the first raw powder is commercially available goethite, and it is dispersed in water with polyethylamine as a dispersant. And in this case, 2 Tesla of magnetic field was no problem. So we applied the magnetic field and just consolidate it and check the phase change during the following thermal treatment. So this is the XRD of as a consolidated goethite. Goethite shows needle-like structure, and with applying the magnetic field, it orients like this. So C-axis of goethite is aligned perpendicularly to applied magnetic field like this. So first we make that the kind of a green cake of goethite, and then we thermally treat it. During the thermal treatment, it changes to the phase changes to alpha Fe2O3. But at 900 degrees C, it is completely transformed to alpha Fe2O3, but it seems to be randomly oriented. But after that, if we heat it at 1000 or 1100, 1200, the crystalline orientation gradually appeared like this. So after the heating of 1200 degrees C, we could obtain perfectly oriented alpha Fe2O3 like this. After heating, we can make that kind of very big sintered body and quite high densification. This is the microstructure, and the XRD of top surface is like this orientation, then the side surface like this orientation. So we can demonstrate that we succeeded to fabricate textured dense hematite like this. This is randomly oriented hematite. In this case, it shows random orientation. It shows quite high textured microstructure. And it shows also anisotropic magnetic property. During the heat treating, the oriented microstructure develops. So after heating 1200 degrees C, for this direction, perpendicular to the C-axis direction, it shows quite interesting magnetic property, soft magnetic property like that. I calculated the mu max from the result. That's mostly equivalent to mangan zinc ferrite. So that is quite interesting property for crystalline-oriented hematite. But if it is randomly oriented, it doesn't show any anisotropic magnetic property like this. But our interest is how is not only hematite, but our interest is can we make crystalline-oriented magnetite? As I explained first, magnetite is cubic structure. I'm sorry, magnetic has a cubic crystalline structure or inverse spinel structure. So actually, magnetite orientation of magnetite is theoretically impossible. But by starting from orientation, go side of orientation, and change it to hematite and magnetite, we thought it may be possible to make crystalline-oriented cubic structure, the ferromagnetic magnetite. So looking at this figure again, reduction of relation of alpha Fe2O3 and Fe3O4 is also topotactic phase transformation. So maybe oriented, if we can make oriented, we can start from oriented hematite, we thought that oriented magnetite could be synthesized like this. But the problem was how we can reduce to magnetite, because the reduction of hematite was very difficult. And we tried to reduce it to stop to magnetite, but even by controlling the temperature, by controlling the atmosphere of hydrogen, but inside was still remained alpha, but outermost surface is reduced to iron state. So I was thinking how we can stop the reduction at the magnetite. And looking at the Ellingham diagram of the phase of iron oxide, here this is the line of this equation, and this is the line of this equation. And to reduce hematite to magnetite, we must keep this state between these two lines. But looking at the temperature and oxygen partial pressure, for example, if it is kept to 1200 degrees C, allowed oxygen partial pressure is among this and this. That means if the oxygen partial pressure is kept in this range, and if the sample is kept to 1200 degrees C, this figure shows it should be reduced, completely reduced to magnetite. And looking at this level of the oxygen partial pressure, I thought this level is almost the same to the normal nitrogen or argon gas, which is purchased by a company. So we just kept the sample in argon atmosphere at 1200 degrees C, and kept about 10 hours. So after the reduction in argon atmosphere, we could make crystalline textured magnetite like this. The top surface shows 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, these kinds of peaks. So, and the side surface, those strong peaks are not appeared here like this. This is a microstructure of Fe2O3, alpha Fe2O3 hematite. So, 1, 1, 1 direction is okay. C-axis direction of hematite is succeeded to the 1, 1, 1 direction of magnetite of this structure. So by using this technique, we succeeded to fabricate the textured cubic structure, the ferromagnetic magnetite. So after making the kind of dense magnetite body, we checked the magnetic property like this. This is the magnetic property of a 111 oriented body measured by a VSM. looking at the value, I think this value is quite high and almost similar to the reported value only for very thin magnetite, only thin magnetite film. So we can make, by using this kind of technique, we can make quite high, quite good magnetic property of a magnetite body in high density, like this. So this is the summary of the phase transformation of goethite, hematite, and magnetite like this. We are applying this technique for making many kinds of thick, thin films, monorays, laminate composites like this. We are trying to apply this technique to many fields of ceramic materials to improving the properties. So if I can collaborate with people who are interested in this technique, I'm very happy to collaborate with you. Thank you very much for your attention.